In this video, we're going to introduce the idea of a limit. We'll use limits to define our major concepts in calculus, so understanding how they work is important. So let's start in this example by considering the function sine of x over x, and let's ask what is happening to the function as the x values are approaching 0. So notice that the function is undefined when x equals 0 because we have 0 in the denominator and we can't divide by 0. In the graph over here, that is indicated by a hole in the graph just to let us know the function's not defined there. So the function's not defined at x equals 0, but we can still look and see what the function is doing as the x values are getting closer to 0. Here we have a table showing what the function values are doing as our x values are getting closer to 0. So I've selected some negative values getting closer to 0 there, and some positive values getting closer to 0 there. And let's see what happens. For the sake of this example, let's plot them on the graph just so we can draw the connection between the table and the graph. So when x is -2, there's our function value. When x is -1, there we are, -0.5. And then from there, the scale gets a little small to be able to meaningfully see what's going on in this graph, but you get the idea. And we have the same thing on the other side. Notice this is an even function. So what we see both from our table and from our graph is that as our x values are moving in towards 0, our function values are moving in towards 1. So we can see that on both sides here. And then we also see it on our graph, on our table. You can see that our table values are getting closer to 1 as our x values are getting closer to 0. So both the table and the graph are telling us that it looks like the function is moving towards 1 as the x values are getting closer to 0. Now this is still a little bit vague. It's not very precise yet. We're looking at a picture and a handful of values in our table and saying, hey, it looks like the function's going towards 1. So we'll make this more precise as we move through the unit, but this gives us the general idea of a limit. An informal definition of the limit says the limit, which we'll call L, of a function f of x is the real number the function approaches as the x value approaches some fixed number we'll call c. The notation for that is we will write that the limit of our function as x approaches some number is L. So for the example we just did, we would say that the limit of sine of x over x as x approaches 0 is 1, because 1 is the number the function was approaching. Let's see an example. Let's use the graph of f of x to find the limit as x approaches -3. So just as we did before, let's see what's going on. So as our x values are approaching -3, and here we'll approach from values greater than -3. Now let's see what the function values are doing. So we'll trace the corresponding function values, and it looks like they're moving towards 2. And we do the same thing from the other side. As our x values are approaching -3 from values less than -3, we trace the function, and again it looks like it's approaching 2. So it looks like this limit is 2. As the x values are approaching -3 from either side, the function is approaching 2. Now, an important thing to note in this example is that the function value itself doesn't matter. So this function is defined at -3. So we can see that f of -3 is 4. So it's defined. In the previous example, it was undefined. In this example, it's defined, but it doesn't matter. It doesn't affect the limit. So the limit is interested in what the function is approaching as the input approaches a given number. The actual function value doesn't matter. What we're going to see is that finitely many things, like the single point of the function's value at x equals -3, does not affect the limit because the limit is interested in the infinitely many function values that are approaching 2 as the x values are approaching -3. In this example, we're given the graph of g of x and asked to find the limit as x goes to 4. So let's start the same way we did in previous examples. We'll start from values less than 4 here. So as our x values are approaching 4 from the left, What are our function values doing? It looks like our function values are approaching 5. But we notice that as x is approaching 4 from the right, the function is not approaching 5. The function values are approaching 1. So our one-sided limits, our limits from the left and from the right, do not agree. So the notation for the one-sided limits is the following. So from the left, we have the limit as x approaches 4, and then we have a negative superscript, and I'll explain that in just a second, of the function g of x is 5. And from the right-hand side, we have the limit as x approaches 4 with a superscript of a positive sign is 1. And this notation comes from the idea that here, if you were to just write out your x-axis here, the right-hand side is moving towards positive infinity, the left-hand side is moving towards negative infinity. So if you're coming from the right-hand side, you're moving from positive infinity, from the left-hand side, from negative infinity. So that explains those superscripts. Now, when the left-sided limit and the right-sided limit do not agree, the overall limit does not exist. So the limit of g of x as x approaches 4 does not exist. And we will use this phrase so often it has its own abbreviation. We'll abbreviate it D and E. And this is an important fact I want to hang on to. In order for the overall limit to exist, the left-hand, right-hand limits must be the same number. If they're not the same number, the overall limit does not exist. We're going to work another example and learn how to deal with this asymptote that's in the function here. But before we do, pause the video and find these 5 values that I requested. These use the techniques we just learned. After you find the values, unpause the video and check your answers. Okay, so we see that from the left and from the right, as x is approaching -2, the function is approaching 1, so the overall limit is 1. That's here, number 3. We see that the value of the function at -2 is -1. That's here on the graph, but it doesn't matter. It doesn't affect the limit. And the other thing you were asked to find is the limit as x approaches -4. So we're used to seeing something weird going on with the graph when we find the limit. That's not the case here. There's nothing weird going on as x approaches -4 from the right or from the left. The function is approaching +4 from both sides. Now let's get to the new and interesting limits. We see the function has a vertical asymptote at x equals 3 that's indicated by the red dotted line. If we want to find the limit as x approaches 3 from the left, this means we need to answer the question, what is the function doing as x approaches 3 from the left? So let's take a look. So here we have our x values approaching 3 from the left. And what is our function doing? It looks like our function is increasing and continuing to move towards positive infinity. Let's pause here and recall our definition of the limit. The limit, L, has to be a real number. We didn't discuss that detail when we introduced the definition, but it's an important detail. L has to be a real number. Remember, the real number system contains all the numbers we know and love, except for the complex numbers. So L can't be a complex number. We will only be working with real numbers in this course. And of particular importance for this example, it cannot be infinity. Remember that infinity, as we've used it here, is just the direction the function is moving towards. It's not a number. So, and this is important, this limit does not exist. For a limit to exist, the function must be approaching a real number. There's no fixed number that the function is approaching. So as x is getting closer to 3, f of x is getting larger and larger. Pretty soon, when we study infinite limits in more depth, we will write that the limit equals infinity or negative infinity when we talk about infinite limits, but even when we do that, it's important to remember the limit still does not exist. So for now, I want to emphasize that unbounded limits do not exist. We can also consider the limit as x approaches 3 from the right. Here, as the x values are getting closer to 3, we can see that the function values are moving towards negative infinity. So again, the limit does not exist. because it is unbounded. And then as we know that if the left or right hand limit does not exist, the overall limit also does not exist. So we've learned that the limit of a function is the real number the function is approaching as the input to the function approaches a given number. And in order for the limit to exist, the function must be approaching a real number from both sides of the given x value. Otherwise, the one-sided limits may exist, but if they aren't equal to the same real number, then the overall limit does not exist.